Dr. Ian, can you hear me? Dr. Ian, I don't know if you can hear me.
Okay, can you hear me now?
Oh, there we go. Yep.
Oh, so sorry. So sorry. Okay, you haven't missed much yet. Apologize. So we are going to finish up this Jupyter Notebook worksheet that I started the last semester in the last lecture, using basic two-layer structure neural network to train a very easy, very fundamental logic function called exclusive OR. We all know exclusive OR. We know what the truth table look like. So how do we use neural network to represent a exclusive OR function? Okay. This is really a two-part notebook. Last time we went through the first part. The first part is really to get you familiar with one epoch, one iteration of forward propagation and back propagation. Okay. So let me just go through it very quickly because you are going to use this in homework 3, which I will review with you very quickly, momentarily. We got to have the activation function defined. You want to set up the neural network hyperparameters and the parameters. So the key part here, obviously, is the architecture, number of layers, and the number of neurons in each layer. I say, so the first part is to calculate forward propagation. Again, use the NumPy vectorization computation. It saves a lot of code, saves a lot of computation resources. And along the way, you calculate the weight, the biases for each layer. This is a simple two-layer architecture. So you have W1, B1, and W2, B2. Okay. And then you calculate for each neuron, for each layer, value Z and A. So Z is the linear combination of your inputs, and A is the activation output, right? Again, all the representation here, as well as in the code, are vectors or matrices. They are not a simple scalar. Remember that. Now, if you look at NumPy code, all of them look like just like a simple scalar operation. So that's the beauty of using NumPy. It doesn't really matter what your argument is. If Z1 is a matrix, the output A1 is a matrix. If Z1 is a simple number, then A1 is a simple real number. Then you calculate the cost function, JWB. JWB is a scalar, but the computation is based on matrix calculation. Multiplication essentially. It's a log loss function. Okay, so that's the J that we're getting, a single number. Then you start to calculate the back propagation. Okay. Again, that's there are 6 equations. So that corresponds to 6 lines of codes to calculate, in this case, DC2, DW2, DB2, and DC1, DW1, and DB2, DB1. Those are the 6 lines of codes that you need to use. Now, obviously, if we have multiple layers, multiple input layers, you have 3 layers, 4 layers. Essentially, you increase the number of lines, but that's not the best way to address it, right? You probably need to, in that regard, is a for loop, but the basic structure is right there. For each layer, you have those parameters you need to calculate. All right, so that's the first part. The first part is an exercise of calculating one iteration of forward and back propagation. So the results really is the cost function. That essentially use that cost function to get the derivative, and you obtain the new updated weights and biases, and use that to go to the next iteration and calculate the next set of forward propagation and back propagation, and go on and on and on. All right, so that process is called what? Gradient descent. Gradient descent. Now, the part three of this worksheet is to use that and run a gradient descent algorithm to find the weights. Find the weights. I give you two cases here. One is used. The only difference between those two cases are just the activation function for the hidden layer. The upper layer, I think the upper layer is all sigma. Now you can experiment on using different hyperparameters. Right now we only have three. I only give you three hyperparameters. The learning rate is the epochs, meaning the number of iterations that you want to run, and also randomizing your initial weights. Remember, we don't want to use 0 or use a large number for our initial weights. We want to have smaller, non-zero random numbers as our initial weights and biases. So those are the three things you can experiment with in this particular worksheets. So I just give you some example. Let's say alpha, meaning that the learning rate is 0.05, which is depends on the magnitude of your input. It may be small, it may be big. Okay, but you just try it on a relatively long epoch and randomize your weights and biases. So rand_dn really is a function to generate random number between 0 and 1, all real numbers. You may or may not want to multiply by factors. It's up to you. I encourage you to do experiments. And B1 and B2 are essentially zeros at the beginning. That's fine. Okay. Then you can run a gradient descent. Okay, so here's the structure that you will experiment on for homework 3. So you create your own, you specify your own epoch, number of epochs, say 100,000 in this case. You need a for loop, and each for loop will calculate forward propagation and back propagation once. So the structure, the 4 module structure of this particular case is a 2-layer neural network are pretty much the same. Forward, calculate forward propagation and get Z1, A1, and A2, and calculate the cost function. And starting from the cost function, you can calculate the back propagation, and you update the weights and biases using the gradient descent. So the structures are all the same. At the end, I want you to keep track of the cost function, so we can observe how cost function actually converge for smaller. Okay, so you pretty much just keep that, accumulate them into a list, simple Python list, then you can get the immediate results. So there are many ways to do this. I just choose to give you a results in every 10,000 epochs. So you see the decreasing of the cost function along the way, right? It is decreasing. Can it decrease more? Of course. Of course, you can run even longer. And this one really doesn't take a lot to run. It's pretty fast because it's a very simple neural network. Okay, so let's say, after we run 100,000 epochs, so I want to check a few parameters at the end. So the first thing I want to ask is, what is the final cost function after 100,000 epochs? So J-1. So for you guys are familiar with Python, what is an index -1 for? You need the last index. So j -1 is equal to j, in this case, 99,999, right? That's your last. That's your last element in the list. So instead of writing a huge number, just say -1. Icon knows it's going to be the last element. So the last element is a relatively small cost function, less than 0.03. Then what we care about is the estimated output, which is A2 in this case, right? It's A2, activation output. So remember our input is 0, 1, 1, 0. 0, 1, 1, 0 because of the scalar plot of a exclusive OR. It's either 0, 0, or 0, 1, or 1, 0, or 1, 1. Camera, it's not even facing us. Huh? I was trying to find a person, but I couldn't find. Oh, hey. So A2 essentially give you an estimate, but it's not hard precision. Remember, this is actually a probabilistic measure of how of the activation outcome. So for A2, the first one is 0.002. The second one and third one are pretty close to 1. The last one is, again, very close to 0. So that's essentially what we want, right? Because we want this to be 0, the first one to be 0, the second and third one to be 1, and the fourth one to be 0. 0, 1, 1, 0. That's what we want. So in this case, if you make a hard decision based on the polarity of the magnitude of the activation output, you can use an RINC. So what is RINC for NumPy?
Based on context, it rounds numbers up.
It's a rounding. It's rounding to the nearest integer. So it's basically rounding. Rounding to the nearest integer. You take that on A2, you get 0, 1, 1, 0. That's your hard decision. Because all those small numbers will be rounded to 0. All the big number close to 1 will be rounded up to 1. So that's exactly the output of 1. So that's just this simple example shows, oh, okay, this training is getting us our desired structure that can actually represent an exclusive OR function. So then the next question is, how does the weight look like? So I want to show you W1 and W2, E1 and B2. So if you look at W1 is a 2x2 matrix. Okay. So it actually the number look very symmetric. They're almost identical in magnitude. Very similar in V1, they are negative in magnitude. Similar property in W2 as well. So you can think about this. If you look at this optimal weights and you compare to homework number 2, one of the problem 2, right? 2B, actually. And you try to get alignment on those things. But it's not a surprise that you will get weights like that. Right? Case 2 is just to change. In this very simple case, it's just to change the activation function from a sigmoid to 10H. And you do the same thing. Just compare the difference. The code is the same. You run it. Again, you ask the same question, what is the final cost? What is A2 and the predicted output look like? Okay. So again, 10H works pretty well. After 100,000 epochs, it's getting really close to 0 and 1. Exactly what you want. Again, the weights biases behave roughly the same as the previous case. I also very much like to see how those two compare in terms of performance. So in this chart, I plotted the loss function against epoch, against number of iterations. So we run a total of 100,000 epochs, right? So that's 10 to the 5. And which one looks like in this case, which one converge faster? It's the orange case. Right? And the orange case is 10H. Sigmoid seems to lagging a little bit. Pay attention that the x-axis, both axes are in log scale. Log scale. So most of the you don't mistake this as really slow convergence. No, it's because we log scaled it. So the first 10,000 epochs, you didn't see a lot of movement in sigma in terms of loss function. But once it kind of catch up to on the right track, they started to go down really quick. 10H happens a little bit earlier. After maybe a couple hundred, they start to drop down. One caveat about things like this is that I cannot guarantee that it will always behave the same way with different randomization at the beginning. You might sometimes run into a randomized initialization that leads you nowhere. It can happen, but you just need to try different types. Go ahead.
That actually happened to me when I was doing the thing.
Okay.
Work.
Okay.
Thanks. I'm off thinking this.
Right. Okay. We're not going to talk about carrots at this moment. So when you start to work on homework 3, you might want to come back to this one. Make sure that you study this. You go to your homework 3. Okay. So let me go to homework 3 and give you an idea of what I'm looking for. So in this homework, I want you to work on the spiral data set. Remember spiral data set? In homework 2, right? Yeah, it is the background. The jupyter file is now detailed. Which one? I thought I did. It's not. Let me double check. I thought I make it visible already. But Tim, what did you check? What did you test on? I thought you said you test on this one already.
Oh, I'm talking about the playground thing.
Oh, okay.
I did the same layout. I just ran it multiple times. And I got different results. Like one time it's on my laptop. It got really good results, and I did my desktop at home. And
Okay.
It didn't work.
This one. Okay. You're right. I apologize. You're right. Yeah, I just turned it on now. Okay, so this is the worksheet in D2L together with Module 2 material. Okay. So the playground. Let's go back to the playground. So this is the data set I'm talking about, the spiral data set. So we use playground to do simulation by changing activation function for homework 2. You change the activation function. You might play around with others, but at least you get some experience with doing the training. So now we are going to use NumPy code we just went through to do the training for this. Do training for a spiral data set. I want to bring your attention to the objective. So make sure you read through the objective and let me explain to you. So I want you to build, I want you to build your own neural network, at least 2 hidden layers, meaning total of 3 layers. So I have to tell you, 2 layers will not work. 1 hidden layer will not. Need multiple layers. So your inspiration or initial idea should come from the playground experience, right? What essentially works. May have built a 4 layer architecture with multiple neurons in each layer, and it worked pretty well. Then you want to build, you want to use that as your basic architecture and implement using the code that we just showed. Okay. So that's my objective. You build your own. Okay. And there's a performance requirements for you. First of all, you need to achieve accuracy of at least 95%, which is not hard at all. You have the right architecture. And I also want you to check the final loss function to be less than 0.05. So those are 2 things that you have to achieve. Frankly speaking, not hard. Not hard. So let me go through it very quickly. I wrote the skeleton of the structure already. And whenever you see notes such as write your code, that's where you have to write your own code. But as long as you follow steps, procedures, and write your code whenever it's necessary, be fine. Okay. So the first step is to create this spiral data set. So I already give you the sub. So you just write a function call. We call it data generator. That will give you your data set. So we need data sets, right? And I also want to plot the spiral data to confirm it look exactly that, like the one that you see on the playground. One step that we haven't really emphasized so far, but I included here, is to normalize the data set. It's a crucial step for any machine learning techniques. The reason that we actually normalize the data set, well, I'm gonna give you a very simple intuition. We get data set with multiple features, right? Multiple features means they come with X1 through X100 to describe a particular data. Not all the features will have the same dynamic range. So what is dynamic range? Meaning the region, scope of the value. Some of them may be very small from 0 to 1. Some of them may be huge between 100 to 100,000. Right? Let's take real estate, for example. A real estate property can have a simple feature such as number of bedrooms. Number of bedrooms is pretty much fixed, right? Small number, a few bedrooms. But you have square footage that's much larger in terms of dynamic range. And you have prices that vary even bigger. When you have input features with a wide dynamic range differences, it usually affect the convergence of your gradient set, because each of those features will diverge in a different speed. You have large dynamic range, large values, it tends to converge slowly, because essentially you only have one learning rate, right? That dictate the overall learning. In smaller numbers, they tend to converge a little bit faster. So there are discrepancies between different features when they have a wide differences in dynamic range. So what we do is a very important first step when you do data analysis, is to normalize the data set. Normalize the data set to all the features, all the dimensions. One of the most popular approach is to do a fancy term called Z-score normalization, but essentially it normalizes the data set to become zero mean and with a variance or standard deviation of 1. Okay, does that make sense? You have very wide dynamic range, but you normalize it, so it becomes zero mean. So there is one. But it doesn't mean it's a normal distribution of X naught. It's just you find out the mean value, you find out the standard deviation, you normalize it accordingly. So this is the simple codes that help you do the normalization. It calculates the mean value for you for the data set. It calculates the sigma, which is the standard deviation of the data set, and you normalize it. So that the last line is a simple normalization. Okay, so we do this. You write code to normalize your data set using that z-score normalize function. Again, I include activation function library that you will be using. Then again, section 2, you set up your neural network architecture. In this case, you start to write your own code to specify the number of hidden layers, neurons in each layer. And section 3 is about running gradient descent. So this is exactly the same as the worksheet that we just went through. Okay. Specify learning rates, epochs, and initialize the weights and biases. Okay. So this is where you need to fit in, write in your own codes. All right. So this is probably the most codes you have to write, but you do have a template. You do have a template. Then you have to think about if you are building a 4-layer architecture. You want to get fancy and build a 6-layer, how would you do? I give you a 2-layer example, right? This is the part that you actually write your own gradient descent algorithms. Then you start to check the output, as I did in the worksheet. Write your codes to find out the final loss function number. Is it fulfilling the requirement, less than 0.05? And check out the first 10 elements of AL. I don't want you to, because this one has 250 pairs of data. I only want you to list the first 10. I don't want you to list all. Just get a feeling what the output activation output is. Right. Print your weights. Then write the predicted outputs. Okay. In this spiral data set, how many classes do we have? How many classes meaning how many different? Is this binary?
Yes.
This is binary?
Those two.
Because we have only what? Blue dots and orange dots. So it's a binary classification. 2 classes. Right. So essentially your predicted output should be either 0 or 1, meaning either blue or orange, right? Nothing else. So again, you can use the same approach as I did earlier. You can use the rounding function to determine the output. We can just end there. I want you to actually look at the performance analysis. In this case, we use very simple performance measure, which is the accuracy. If it was actually a blue dot and you mistakenly classified it as orange dot, that's an error. An error. So this is where I want you to calculate the number of errors in your estimate based on the predicted output. And this is where 95% comes in. You having an accuracy performance of 95%. So this is where you plot the curve of loss function versus epoch. That chart that I showed earlier. I already give you the matplotlib codes, so you just execute. You just need to execute. The last one is fun. So what does the decision boundary look like? You play with the simulation in the playground. They give you decision boundary, right? Now I want you to visualize the decision boundary here. Now I know it's too hard for you to write your own codes. So I give you most of the script, but you need to fill out your own model, which in this case is included in the full publication. Basically, you write your full publication here. Because in this case, we don't need back publication. In this case, we just need to have the final weights and biases, right? And pass the data to the model, and that will map the value to the scalar part. You will use that approach to find the boundary. Okay, this will actually justify whether you actually did the job or not. If you get a 100% accuracy, your decision boundary will be pretty clear. All right, question? This is a simple one. Okay, wait until the next one. Huh?
What's the next one?
The next one you will use carrots and a lot of different training. This is just the beginning. So use your worksheet, exclusive or worksheet to work out this one. This is a warm up for the next for forward number 4. All right. I want to move on to the next topic. Up to this point, we haven't really touched upon exactly what is the training. Okay, we know the training process already. We study the classical neural network, the loss function, no gradient descent. But exactly what is machine learning? So I want to use this module to give you more details and set up a framework for machine learning process. And during that process, we will run into issues, and most of the significant issue is overtraining, overfitting. And it's a very common mistake. I mean, shouldn't say mistake, just a pitfall. When you train, you try to get the best results for your training data. And it doesn't really apply to other regular data. So that's called overfitting. And there are techniques called regularization technique to alleviate the issue. But this small module is really about setting up the machine learning workflow and using some of the techniques to deal with issues such as overfitting. Let's get started. So a couple questions about training neural network. Okay. How do we actually optimize the model for the best training performance? We know that. We use gradient descent, right? We use gradient descent to optimize the model for the training performance. But the second question is more important. Once we have that training model, how do we know if this model can actually apply or generalize to new data, unseen data? The first step really is to give you a known data, known output. You start to train to get the optimal results. But the second one is more important. Once you have that training model, can we apply that and generalize it, get similar performance on new data? That's essentially what we need to achieve, right? So there are two things that we are doing for any machine learning algorithm. Which the first one is optimization. You try to find a model that you can fit most of the training data. That's our first. That's only the intermediate goal, first goal. The real quest is to find generalization of the model to new data. So that's what I want you to remember this. So with that in mind, let me just give you a very simple machine learning workflow that I've been using it for undergrad students. I think it applies. Just in general, there's really not a lot of complexity in this things. Right? It can be simply explained by a few steps. Over here, we don't do a lot of data acquisition or pre-processing. We focus our effort mainly in the box close here, the dotted box here. We collect data, whether this data is available to us or we actually go out and collect our own data. There's usually some pre-processing we need to perform. Okay. For those of you who already have some experience, that means get rid of some of the bad images, for example, or you actually augment your image set with different variations. Okay. A lot of different techniques come into data pre-processing. But when the data is available, we started to split the data into two paths. And the bottom path is the training path. It's the training path. And the upper path is the testing path. So training path, we kind of understand it. You feed the data into the network model, you train it using gradient descent. You come up with a model. Now, in order for us to generalize to unseen data, we actually need some unseen data, right? New data. So that's the upper path, test data, that's separate from the train data. And use that test data to verify whether we actually have a good model that's generalized. And this process is actually an iterative process. Until going through several iterations until you find a model that actually that's good for training, have good training performance, but at the same time also generalized to testing. And finally, we deploy the model. What does deployment mean?
Actual application.
Actual applications, right? We train a facial recognition model. It works on a computer, but does it work on a Raspberry Pi, a Ring camera, right? That's the deployment. That model is deployed into a device that can actually recognize the face. Right? So that's doing different things because it is this once you deploy, the job is pretty simple. It's classifying, doing classifications, it's doing recognitions. Before deployment, all the effort is to train the model. So you heard people talk about in the industry talk about it takes a lot of money to train a model. Hundreds of millions, if not billions of dollars. Right? People build data centers to train data. Most of the effort and the computing power really is spent on training the data. Once you have the model deployed, the effort compared to training is much smaller. And this part is called inferencing. So inferencing. Right, let's focus on this iterative process first. And we have a term for that. It's called train test loop. Okay. So what exactly is a train test loop? Here is the first step. The first step is you split your data into two sets. First is the train data. The other one is the test data. So once you have that split, then they naturally go to the upper path and the lower path, right? The train path and the test path. The rule of thumb, maybe we use roughly 70% of the total data set training. So if you have 100,000 points, and you use roughly 70,000 of them as your trained data. So that's the first part. And the second part is our unstained data that we want to test whether the trained model is a good one that can be generalized. So we usually reserve the remaining 30% for test purpose. So that's the split of train and test data split. Now there are a lot of techniques involving this the splitting method. Usually you can assume you randomly split them. Okay. You randomly split them. But there are some finer details in using the test data. We'll see in our data pipeline later when we do the training, we actually allocate a small amount of data from the test data, and we call it development or validation. We call that validation data. Okay. It's that this small green color bar here, roughly 5% of the overall data set. And use that to go with your training process and use that to give you real-time performance evaluation of the test result for each epoch. Let me say it again. So you are doing in each epoch, potentially in each epoch, you have a set of weights, right? And you can use this weights, the new model, and use the 5%, small 5% validation data to validate at that junction whether you are generalized enough. Okay. So kind of a real-time feedback during the training process. You don't wait all the way until you finish the training, and you apply that 20-25% test data and realize, oh, you didn't do a good job, right? So you want real-time feedback along the way. Okay. So the second part of this split, and we split the test data further into the green bar, which is development data, 5%. And the rest is the real test data that you reserve at the end of training for the final system analysis and performance analysis. Okay. Does it make sense? And frankly speaking, why we do this is because we want to avoid overfitting. But we'll talk about what's overfitting very quickly. Okay, kind of a simple way to formalize what is a machine learning workflow. The first step we just explained, you split the data set to training and test data. That's first step. The second step is just to train and predict. So you look at the training data, you try to train and fit. Train and fit really pretty much means the same thing. It's the training process. And we say fit because we want to fit the test data to a model or vice versa. We want to see if all the training model actually capture most important features of the data set. Then, but the second part of step number 2 is to predict. And the predict is to use the test data to make prediction using the train model. The step 2 pretty much is the biggest, is the bulk of the processing that involves both the train data for training and predict, and involve the test data to do the predict portion. And the next step is to calculate the performance of the model. Okay. We evaluate the performance of the model. At the end of the day, we look at error matrices. Different machine learning algorithms have different error matrices. For classification, that's pretty straightforward. Accuracy, obviously, is straightforward, whether you correctly classify the data points or not. But there's also false alarm, right? False alarm go both ways. The correct one that you incorrectly, but a blue one you incorrectly put into an orange one, right? And vice versa. So we look at that closely. Then the iteration starts. You repeat the process. You repeat the process until you find satisfactory results. Okay. Now I want to look at. I want to explain what overfitting and underfitting means. Let's just look at this very simple illustration for the performance of your training data versus your validation data. So this is very similar to the chart that we show in the worksheet. You can think about the y-axis, the error, as the cost function. This cost function is essentially an error measurement, right? The residual errors. And training time is, you can think about that as epochs. Your training performance usually is behaving as you expected. If you train it correctly, the error will be smaller and smaller. Whether it's accuracy or it's a loss function, it's getting smaller and smaller. Okay. But the validation in general, the red dashed line is the validation. Remember, the validation is that 5% small amount of data that give you real time a reflection of how well the data is generalized. So I don't think it's a surprise that the validation data actually can perform in a fashion like that. Doesn't really follow performance of the training performance. Okay, so let me ask you a question. Okay. Intuitive. Which one of those two data sets should always perform better? Is it the validation data or the training data?
I have to match the training data most of the time.
Sure, that's straightforward, right? Has to be training data because we use training data to train the model. Validation data is a completely new data to the model. So validation data is going to have more errors, perform worse than training data, that's for sure. But what we really want is a result that validation data kind of follow the trajectory of the training data. Right? If it goes down, it should go down. But of course, we can tolerate that it performs a little bit worse. But if something like that happens in this particular illustration, the validation data actually started to diverge in terms of performance. And you know there's something not quite right. And this is a classical overtraining scenario. Go ahead. Coming from what? The test. Yes. Validation data is coming from the test data, which is not seen by the training process. So I use this blue line indicate the divergence starting to happen, right? And we can say on the right-hand side, overfitting is starting to occur. Your training is getting better and better, while your validation is not, actually getting worse. So this means that you try too hard. Your model is trying too hard to fit the training data, but it's not generalized. So that's a concept. And actually very realistic because you are going to see those things. See the behavior like this when you train your own model. Okay, so let's explain those two phenomena, two common issues, overfitting and underfitting. Okay. Before that, let me give you some other terms to digest. One is called bias. Other one is called variance. Think about both as statistical terms or estimation errors, but both of them are not good. And they means that you have some errors in your estimation. So what is a modeling error? A model has bias. So I put some definition here. So bias is coming from erroneous assumption, meaning wrong assumptions in the learning algorithm. For example, some of the high biases can come from you ignore a very important feature. Feature is very important in determining the, for example, the housing price, right? You ignore that. Then your training model will eventually deviate from the important information. When you lose an important information, your results tend to go the other way. That's called bias. Variance, on the other hand, is the modeling error when you start to see high sensitivity to small changes or small fluctuations in the training data. In plain English, this means that your training data cares too much about small variations in the data set. Let me say it again. Your training started to pay too much attention on small fluctuations of the data set. There are several reasons why data set cannot be totally trusted. First of all, it's not completely clean, right? Some data set can have errors. So that pre-processing is very important. We want to get rid of outliers, bad data sets. But still, there are some data just noisy, a little bit noisy. That could be random noises. Okay, it may not be intentional noise, but just random noise. So that's called variance. So if you think about variance as the changes from the data set with respect to the norm. Every data set, if you think about it, there is a mean, there is a variance. Right? If you are within this variance, this is normal. But if you are outside of this variance and you're far away from the variance, those are the sensitivity. Those are the small fluctuations that we tend to ignore in the big picture. Okay. But anyway, bias and variance are the key errors that can come from modeling. Okay. So we use those two concepts to explain overfitting and underfitting. Okay. Now I'm going to give you some visualization. How many of you actually own a gun? Did you go to a shooting range?
Earlier this year.
Okay, all right. So if you have experience, I don't own a gun, but I've been to shooting range before. Okay, so if you go to a shooting range, let's give a more common experience, which is go to throw it, like go to a bar, especially English people, right? In the English bar, they have a dart, so you can throw a dart. Right? So that's essentially shooting something, right? Shooting at something. So let's say you are shooting at you're at shooting range and you want to hit the bullseye, hit the target. So if you are a good shooter like Tim, this is a very good result. Right? So if you use the term bias and variance, this has very little bias. Why? Because it's on the bullseye, right? Around the bullseye
together.
And they're bunched together. Right? Okay. Bunching together actually means low variance. It's very low bias because it's right around. It's all pointed in a center. In this case, this is what we want. We want a low bias. We want our model to be low bias and low variance. Now, how about this one? In terms of bias and variance, what's the bias? Do you think if this one is a low bias or high bias or medium bias? The shots are scattered, but all the shots seems to be averaged to 0. So in that case, the bias is actually pretty low, if you think about it, because the guy's actually trying to aim at the bullseye. For maybe he has a bad form. The shots get a little scattered. But it feels like if you average out all the locations, it's actually close to 0. So in terms of bias, it's actually pretty small. But how about variance? Obviously, this one has high variance, right? Very high variance. Now, how about this one? This guy is accurate, but accurate in the wrong way.
High bias
Very high bias.
and then low variance.
Maybe you know he only have one eye. Keep shooting on the left hand upper left corner. But variance is pretty small. It's very concentrated. Questions? Ideally, if you are focusing on the bullseye, and even though you are a bad shooter, so it should scatter around. So when you average it, yes, it is close to 0.
This one is like it's the size of the block accurate.
Yeah,
The size.
yeah, exactly. It's a good shooter, right? Maybe you just have some feedback in his eye, or he has bad form that day.
I guess the rifle is not sighted in. That'd be probably the actual correct answer. It's
Right. Yeah, his gun needs some calibration. All right, the last one. What do you think? Yeah, so obviously not low bias, right? And also variance is high. This is pretty bad. Okay. So that's modeling error, biases or variances. So biases actually in the machine learning term is actually we call it underfitting. It's underfitting. But if you have a lot of attention on trying to fit those small variances, that's overfitting. So I'm going to give you a couple of visuals to explain underfitting and overfitting. So we have a lot of orange points in those 3 charts. They are all the same. Now we can use different classification. We can draw different boundaries to classify them or try to fit all those points. On the right hand side, you have a very easy linear regression line. Obviously, it's not very accurate. A lot of points are not covered, right? So in that case, that's around the fitting. And the middle one seems to be doing better because it's a kind of a second degree polynomial, right? Okay, upward. And you can see the distance between the orange points and that regression curve, it's getting smaller. So the error for the middle curve should be smaller than the one in the right, right? So in that case, we call this, right fit, right? The third one obviously is overfitting because we are using a 4th degree polynomials, trying to fit a whole bunch of points on this charts. Now in this case, in terms of this regression model, it has a high variance. because we try to pay attention to a lot of the changes in the data. So that is a case for overfitting. Okay. Now this one is pretty much the same. If we, this is classification, right? We want to classify the blue dots from the orange dots. First one is a simple linear regression. So a lot of errors. We underfit it. Right? This one is absolutely underfit because you are going to get a lot of errors, a lot of classification error. The second one looks moderately complex, but it missed a few points on both sides. But it's much better than the one on the right, which is fully underfitting. So this one will have a much better accuracy performance. So it's called that right fit. The third one, again, try very hard to separate the blue from the orange. Now you can get 100% correct in this case. But if I add more data points on this scatter plot, it will fail, not failing, but it will get a lot of inaccuracy quickly. So in this case, it obviously has a very high variance, and that's what we call overfitting. Right? Based on this understanding, I want to kind of start to talk about how we address those issues. So underfitting is easier because most of the time, because you miss a lot of the underlying structure of the data set. It's the opposite of overfitting. Overfitting is paying too much attention. Underfitting is paying too little attention. Okay. So you either increase the model complexity by adding more neurons, adding more layers, okay. Increase the number of features. This is coming from the standpoint of processing the inputs. Right? Some of the features you might want to include, right? Not dropping important features. You also may want to remove some of the outliers. Of course, you can always increase the number of epochs or increase the duration of the trainings. So underfitting is not that hard to do. Okay. Overfitting, on the other hand, is our focus. Okay. So I highlighted regularization. Okay. That's what we want to focus on. We want to use various techniques to reduce the value of weights. So that is a simple sentence, but with a lot of meaning. Okay. But basically, you want to make sure that you are not putting a large value on particular weights that you want to overfit it, you want to overtrain to fit all the data. So we will talk about this starting from next Monday. Okay? This is our focus. Okay, I want to give you a few examples to give you some intuition on the general issue of overfitting. So this example is pretty simple. I'm just a hypothetical scenario. So let's say you are a production manager, the chip company, for example. You're producing microcontrollers. So this microcontroller has only 2 parameters when you do testing. Simplified case. So when you measure X1 and X2, and you come out with a scatter plot like this, the red dots means that it's good one, and the blue dots means that it's been rejected. So you measure X1 and X2, you come out with classifications of either reject or accept. Now you are the production manager, and you are given those data sets, and you have your engineers or yourself plot this scatter plot. How do you actually come up with a method to actually determine Can you find an algorithm to classify, uh, you know, future points, future data sets? How would you do this? Let's say you don't have neural network background yet. Right? If I were the manager, right, I'm just going to kind of start to circle, right? I think from my first observation, most of the blue dots are in the outside, obviously. They are enclosing the red dots. So I could probably draw kind of a circle as my initial decision boundary. That's the term I'm trying to get, a decision boundary. But obviously, that's just intuition. But right intuition needs to be refined. So now you learn neural network. What would you do? That seems to be right, but how do we actually use neural networks to classify? Okay.
That boundary that we said will draw to
Mhm.
calculate like variance and all of those, and see what sacrifice we have to make.
So obviously, a circle is curved, is kind of a right intuition, right? But now you are in the fifth week of neural network class. You should be able to tell me how to achieve that circle. How do we get that circle? Do you remember when we taught the universal classifier?
Yes.
What's the universal classifier? Right? Each neuron, especially low-level neuron, they are essentially the linear classifier. Remember? So a circle is what?
A bunch of.
A bunch of classifiers, right? A bunch of classifiers. So that's the basic concept. And at least you know you can use a two-layer neural network with a lot of neurons to build this. Correct?
Yes.
Make sense? Right. So if you don't remember, let's go back to your notes, please. All right. Okay. We have 5 minutes, so but at least let me push through a couple more pages. So now you wear your neural network engineer hat. You are a neural network engineer now. Okay. How would you solve this? How would you solve this? Right. Now remember the machine learning workflow. Okay. So what is machine learning workflow? The first step is to split the data, right? You are given 200 data points. Now Dr. Lin says we need 70% of it for training data, 30% of it reserved for testing. So you split it first. Okay. Let's practice this, okay? Then we start to experiment with different neural network models to see the effect, from the complexity of the neural network. So I'm gonna say, simple, baseline, complicated, or types of neural network, okay? We will look at very simple evaluation metrics, just accuracy. Okay, at this moment. All right? And we want to observe the model performance on accuracy in training data and test data, okay, so we can get a comparison. All right? Let me at least give you a really bad case. All right, so this one is baseline, simple, not even baseline. One hidden layer, and I only have 4 neurons in that hidden layer. So we have total of 5 neurons, right? Okay. And I use ReLU in my first layer activation. In the upper layer, I use sigma because this is binary classifications, right? So I'm going to use sigma. So that's your basic structure, very simple. All right, now I give you the results. That's the decision boundary. Why? Why the decision boundary look like that? Because how many neurons do we have? So I don't know where the fourth one is, the fourth line is, but We know there are three of them. Right? Now, of course, I didn't. I actually ran gradient descent and come up with this. Maybe I didn't find the best parameters, but that result is actually predictable. We only have 4 neurons, right? So how bad is the performance? Only 54% accuracy. So this is a classical underfitting, not sophisticated for this data set, even though this data set doesn't look very complicated, right? So what will be your next approach? What do you think? Exactly, right? Now you think like oh, okay, let me finish this. So the test data, I use the 30% for test data. The accuracy for the test data is only 51%. This is really bad, right? It's 50. You're like tossing a coins. All right, so now I'm going to give you a more reasonable baseline. That's just my approach. I say I'm going to use 10 neurons in the same 2-layer architecture. I like it, right? That's more like it because you do see roughly 10 linear classifier combining together. I mean, a good classifier. Okay. Reasonable? In this case, there's no underfitting anymore. And we calculate the accuracy for the train model. A train data is 83%. And we use that to do our validation on the test data. It's 81%. Now it's getting reasonable. This is the baseline. We can make it a little bit more complicated. 23 layers, 2 hidden layers. The first hidden layer is 20. Second hidden layer also have 20. And both of them use gradient. Now your decision boundary look a little bit more complicated. But you get better results. And in this case, the test data is not that good. It's not far off. Remember, the baseline model is 81. Right? So you start to see the trend. You have a more complicated neural network. The training performance continues to improve from 83 to 90, but your test data does not. So we start to see what? Give me the term.
Overfitting.
Overfitting. Right, correct. This last one is even more dramatic, right? I just, give 100 neurons and train it, and you get 100%. Trust me, right? You get 100%. But what do you think will be the test data results? 75. This is not a big sample example, right? Because we don't have a lot of test data. It's only about 30%, right? I think it's less than 50. But again, you see the overfitting occurring, right? So the key takeaway is you can train your model to be 100%. You can absolutely do that as long as you have more neurons, more layers, more neurons. But at the same time, you need to be mindful of the generalization process. You want to avoid something like this. The test data doesn't really give you more performance. Okay, let's stop right here. Take this idea, digest it. We'll continue next Monday. All right.